So our do now is specifically asking us to solve the quadratic equation below by completing the square. So we want to find the roots. So a little mixed review for us in that completing the square. Remember, when completing the square, we always want to make sure our a value is equal to 1. It already is, so we don't need to do anything with that. It's in standard form. So our first step is going to be to move our constant to the right side. So now we have x squared plus x equals 6. The next step is probably the most important step, which is actually completing the square, meaning that we are going to add b over 2 squared to both sides. Our b value in our quadratic in standard form with a equals to 1 has a b value, a coefficient of 1. So b over 2 squared is going to be 1/2 squared, which is 1/4. And like we discussed, we want to leave that as a fraction. So we'll add 1/4 to both sides, giving us x squared plus x plus 1/4 equals. Now 6 plus 1/4. We don't want to make that a mixed number, 6 and 1/4. We don't want to make that 6.25. We want to leave it as an improper fraction, 25/4. This way, in our future steps when we're taking the square root, we can see if we have any perfect squares. Now that we have a perfect square trinomial, we can factor it. Perfect square trinomials always factor in the form of x plus or minus squared, where that constant value is always b over 2. So in this case, that's going to be plus 1/2. So x plus 1/2 squared equals 25/4. Our next step is to take the square root of both sides. Taking the square root of the left side undoes that exponent. We don't need those parentheses anymore. And now we have x plus 1/2. On the right side, 25 and 4 are both perfect squares, so we can take their square roots, giving us 5/2. But not just 5/2, plus or minus 5/2. Our next step needs to be creating our two equations, where in one case, x plus 1/2 is equal to positive 5/2, and the other where x plus 1/2 is equal to negative 5/2. And then we can solve each, which works out lovely. 5/2 minus 1/2 is 4/2, which is 2. And negative 5/2 minus 1/2 is negative 6/2, which is negative 3. So two real rational roots. Today we're going to start looking at what we call linear quadratic systems, or quadratic linear pairs. That means we're going to have on the same coordinate plane, or in the same system, both a quadratic and a linear function. There are 3 types of solutions we can have. You can have 2 solutions, meaning 2 points of intersection. 1 solution, and in that case we say the line is tangent to the parabola or the quadratic, or we can have no solution at all. Very much like our systems of equations, we can solve these by either graphing or taking an algebraic approach. Today we're going to take a graphic approach. Okay? So again, we're just showing our 3 options of solutions: 2 solutions, 1 solution, or no solution, meaning the line and the quadratic do not intersect. Okay? So our first system, we've got f of x equals x squared plus 2, and g of x equals negative 3x. G of x is linear. We can graph that right away. It's in slope-intercept form. We can see that the y-intercept is the origin, and then our slope is negative 3, so we're going down 3 to the right one, down 3 to the right one, down 3 to the right one. I always like to graph the linear one first, because I think it gives me something to make sure, like kind of a framework of where my quadratic should be or shouldn't be. So we've got g of x equals negative 3x. So now we've got a graph f of x equals x squared plus 2. We can do this by hand. We know how to do that. We find the axis of symmetry, so we can find the vertex. We have the y-intercept, its reflected point. We can solve to find the zeros, and we get our 5 numbers to make our nice graph. But yes, that'll get us a nice quadratic, but it does not guarantee that it'll include the point of intersection. So to guarantee that we're going to include the point of intersection, we're going to put this into the calculator to see the points of intersection. So we're going to our graphing calculator to use that to get our information we need in order to graph our quad linear system, particularly for our quadratic. So we're going to go to y equals. In y1, I'm going to put the quadratic equation, x squared, make sure to arrow out, plus 2. Okay? And then below it, y2, negative 3x. To get our picture, we're always starting with zoom 6. Okay. Now, it might be a little tough to see the points of intersection because the size of the screen, the pixel nature of the picture. Remember, your calculator is not in HD, it's only so limited, but I can see like 2 points of intersection, one here and one here. Okay. The calculator can actually calculate that for you. I'm going to show you how to do that, but it's not really the focus of our lesson. Okay. So we can do that by going to second trace to our calculate window and using 5 for intersect. Okay. Now the calculator asks me, is this first curve? Yeah, blue is y1. Second curve? Yes, red is y2. And now it asks me to guess. This guess question is more important here than we saw it with our linear systems because we could have 2 points of intersection. So with my guess, I put it towards the point of intersection I want to see. Okay. And it gives us negative 1, 3. So that's one of them. To find the second one, I'm going to do the same thing. Second trace, go to 5 for intersect. Okay. First curve, yep, second curve. Now I have to make sure the flashing icon goes closer to the second point. If I leave it there, it's going to give me that same point of intersection of negative 1, 3. So I need to get it up there, push enter. And I can see, oh, there is a second point of intersection. It's the ordered pair, negative 2, 6. And that's great to know, but it doesn't give us enough information to graph our quadratic. So to get that information, I want to go to the table to find a table of values. So we're going to go to second graph to get our table of values. Okay. So one of the things I want to notice in the table is I want to be able to identify where those points of intersection are. Okay. And what I'm looking for in that table is where the y values are the same. So if we look, when x is negative 1, the y values for y1 and y2 are the same. When x is negative 2, the y values for y1 and y2 are the same. That's unique to those 2 points. It doesn't occur anywhere else. So that tells us these are our points of intersection. So now we're able to find points of intersection just from the table. We should include these 2 points in our table of values when we graph. We should also include our vertex point. Now remember, vertex point is our minimum or our maximum. Our quadratic opens up, so it's a minimum point. Blue is our quadratic, so I'm looking for where is the y value the smallest to find the minimum. And that's right here at 2. So the ordered pair 0, 2 is our vertex or our minimum. To make a nice picture, we want 2 more points on the other side of our vertex. So we might as well use the reflection points of our points of intersection. Okay, and those will be the 5 points we use to create our graph. Our 2 points of intersection, the vertex, and those 2 symmetrical points. So those are what we're going to write down in our booklet. So from our calculator, we're going to take those values we saw as important, our vertex, our points of intersection, and our reflection of those intersection points, and we're going to put them into a table of values. So x and f of x, or x and y, and that was for f of x equals x squared plus 2. So our first points we put in were our points of intersection. For my notes, I'm going to label for myself, we're putting this here because it's the point of intersection. That's why we chose to put it in the table. Okay. Also, always including our vertex, our turning point, in this case, our minimum. That's an important part of our graph. That's why we're putting it in the table. And then our reflections of our 2 points of intersection, just so we have a nice symmetrical graph. Okay, and we can graph. So I always start with the vertex. We've got 0, 2. Okay, let's see, -1, 3, -2, 6, 1, 3, and 2, 6. Okay, so we can make our nice quadratic. With having that line already graphed, we kind of know where to put the quadratic. We're going to label. And then we also want to identify our points of intersection. Right, so that was -1, 3 and 2, 6. And that's our answer. So that's what we're putting down and boxing as our solution. -1, 3 and -2, 6. That's our answer to the system. The 2 points on the coordinate plane for which both functions have the same value, for which you input an x, you get the same y value, or the same f of x, g of x. Okay. So on our next system, right, slightly different. We've got m of x equals x squared minus 6x plus 3, and n of x equals 2x minus 3. Minus 13. Minus 3 would be easier. So we want to notice in our linear one, our y-intercept is not on the graph. Okay, so we're going to need the calculator to get 1 point. Once we get that 1 point from the calculator, then we can just use our slope. It'll be nice and easy. So we're going to use the calculator to get key information for both. For our second system, we're going to go back to y equals, and we're going to clear everything out. In y1, again, I'm going to put my quadratic, x squared, arrow out, minus 6x plus 3. And then our linear, 2x minus 13. We're going to go to zoom 6. Okay. Looking at this picture, the nature of the picture, how pixelated it is, it's really hard to tell if there's one intersection point or if there's two. And that's where that calculate intersect and using the table can really come in handy. So what I would do is do my second trace, go to 5 for intersect, first curve, yes, second curve, do our first guess, and it gives us this point of intersection here. Now, it doesn't give us 4 perfectly. It gives us 4.00002. The reason the calculator doesn't give us 4 as an integer, because the way it calculates this is it's calculating the distance between the individual pixels, so it's not perfect. So we have to know the calculator really means the point of intersection is 4, -5. To check and see if there's a second point of intersection, I'm going to go back and do the point of intersection again, but put my guess further away to see if there's a point of intersection further to the right. And there's not. It's still 4, -5. And we only did this because it's a little hard to see. Okay? So we know now there's only one point of intersection. So in our table of values, I'm only looking for that 1 point. So I'm going to go second graph to table. We said our point of intersection was 4, -5, which we can see right here, the one ordered pair where both y values are the same. Okay? We needed the calculator to also find a point on the coordinate plane to graph our linear line. Why not just use that point of intersection and then use our slope? Okay. So in that, we've got 1 point for our line. We've also got our first point for our quadratic. We always want to include our vertex. So again, our quadratic is opening up. So I'm looking for the minimum value. Okay, where do my y values start to change? Right, they're going down and then all of a sudden they start going up again with our minimum y value of -6. So 3, -6 is our vertex. Okay. Just like last time, I'm also going to use the reflection of our point of intersection, which is 2, -5. But we still need 2 points. So these last 2 points are really up to you. It could be 1, -2 and 5, -2, it's reflection. It could be 0, 3, and it could be 6, 3. Just things that fit on our coordinate plane. For me, I think I'm going to use 0, 3, and 6, 3. I think that'll get us a nice picture. So that's what I'm going to go with and write in my table. Again, we just chose those because we needed more points. Okay, so from our calculator, right, first thing I'm going to jot down, just because it's easier, is doing that linear function, x and n of x, okay? And why not just use the most important point, which is our point of intersection, okay? So finding 4, -5, 1, 2, 3, 4, 1, 2, 3, 4, 5, and then using our slope of 2 to finish our line. And we'll leave. Now our quadratic. So in our quadratic, now we have x, m of x, and our key information. Okay, so key information we took, we had our vertex, 3, -6. We had our intersection point, 4, -5. Its reflection, 2, -5. And then remember, those other 2 points were points we picked, another point and its reflection. So I picked 0, 3 and 6, 3 to get a nice picture. And then we're ready to graph. Right, so starting with the vertex, right, there's our 3, -6, 4, -5, our point of intersection, 2, -5, 6, 3, and 0, 3. Right, and I'm trying my best to curve and also show that it's not intersecting again. Like we saw in the calculator, it was a little hard to see that it was only intersecting one. So your picture doesn't have to be perfect, but do your best. Then our next questions are really asking us, kind of going back into that function notation, is m of 4 equal to n of 4? Well, yeah, right? Because an x value of 4 is where our point of intersection is. And we can see it in that table. When x is 4, n of x is -5. When x is 4, m of 4 is -5. So they are equal. And then that also answers our next question of what is the point of intersection. That was the ordered pair, 4, -5. So we have one solution. The line is tangent to the quadratic. Okay. So our last system we're looking at, we've got quadratic and linear again. Y equals x minus 3 squared minus 8, and y plus 2x equals -6. So you may notice, or hopefully you notice, our linear equation is not in slope-intercept form. So my first step is going to be to get that into slope-intercept form. So not only can I graph it, but so we can put it into the calculator too. Our equation has to be in slope-intercept form to put it in the calculator. Okay, so here we go. Y-intercept of -6, slope of -2, and we label. Okay. Now you might be thinking the quadratic, ooh, that's not in standard form. Correct, it's not in standard form, but it's in a form we can put it into the calculator, and since we're using the calculator to find those key values, I don't think it's necessary for us to put it into standard form, so we can just leave that. Our last system, again, we're going back to y equals. Putting in our quadratic, it's fine with x minus 3 to the second power. Arrow out of that, minus 8. And then our linear function in slope-intercept form, negative 2x minus 6. So we're going to go zoom 6. Ooh, and look, we don't have a point of intersection, so we have no solution. Okay. So at this point, all we're going to do is use the calculator to get a table of values to graph. Okay. So going to our table, not looking for a point of intersection because it doesn't exist, we're going to start by looking for the vertex. Right? So remember, blues are quadratic. Again, it's opening up, so I'm looking for a minimum. I can see that here with 3, negative 8. So there's our vertex. Right, so we're going to use this point. Okay. Might as well use our y-intercept. We can see it. Okay, don't necessarily have to, but it might be nice. And then it's reflection. And then we just need another 2 points. So I think I'm going to use, why not use 4, negative 7, and 2, negative 7. Could have used 1, negative 4, and 5, negative 4. Could have used 7 and 8, and negative 1, 8. Right? It's your choice. We should get the same picture either. Right. So putting down our key information from our calculator, and since this has no solution, we saw it doesn't have a point of intersection, we really had a little bit more freedom in terms of the values that we chose. Obviously sticking with our vertex and then going from there. And so our vertex was 3, negative 8. And then from there, I chose the points 2, negative 7, 4, negative 7. Might as well use the y-intercept 0, 1. And its reflection point 6, 1. And then we're able to graph. Okay. So again, as always, starting with our vertex. 4, negative 7, 2, negative 7, let's say 6, 1, and 0, 1. Labeling, and then we've got to state our solution, which is that there is no solution. In the classwork, same idea, right? If you can graph the linear, go graph the linear, using the calculator to see is there 1 point of intersection, 2 points of intersection, so on, and using that table of values to come with our key information.